In the early 1970s, expanding digital networks began generating volumes of information that engineers struggled to organize into large, shared databanks. Looking at the physical footprint of early mainframe computer units, the scale of the hardware is obvious. But at the time, these systems lacked a universal, logical framework to relate massive datasets to one another. The theoretical solution arrived in 1970, when Edgar Frank Codd published a paper titled A Relational Model of Data for Large Shared Databanks. To translate Codd's paper into working software, IBM researchers Raymond Boyce and Donald Chamberlain developed a new programming language designed to execute his relational theories. This programming language, built to organize these massive arrays of physical data storage, was initially known as SQL. While Codd established the mathematical logic for these relationships, SQL provided the practical syntax needed to implement them. This turned an abstract concept into a functional tool for managing information at scale. That original acronym eventually evolved into SQL, which stands for Structured Query Language. Developers commonly pronounce it as SQL or SQL. Both pronunciations are equally valid and simply come down to user preference. As computing networks expanded, so did the need for standardized communication, a role filled by the American National Standards Institute, or ANSI. ANSI officially recognizes SQL as the standard language for relational database management systems. Because of this recognition, almost all major proprietary database platforms rely on it, including Oracle, Microsoft SQL Server, Sybase, and Access. While these vendors incorporate their own proprietary extensions, the core standard SQL commands function consistently across all of their systems. Mastering this core syntax gives developers a universal toolset to architect and query almost any major corporate database in the world. This universal functionality is driven by 6 core SQL commands: select, insert, update, delete, create, and drop. These commands can accomplish nearly everything a database requires. But the strict rule of relational databases is that physical architecture must be completely established before any data can be stored. The foundational constraint of that architecture is the establishment of data types. A data type dictates exactly what specific kind of information is permitted inside a single field. This prevents data corruption at the point of entry. The system will automatically reject a text string if the developer instructed that field to exclusively hold numbers. Developers must also define precise size limits within these data types to maximize storage efficiency and prevent overflow errors. To physically instantiate these theoretical parameters, developers rely on the create table command. Data types operate as rigid, unyielding physical laws that guarantee the mathematical integrity of the entire database. Constructing a new table requires developers to use an exact syntax logic. The command starts by stating create table, followed immediately by the exact target name for that structure. The code must then define the fields, which act as the vertical columns of the final grid. Every single field listed must immediately be assigned its governing data type. Size limitations are written inside parentheses next to the data type to restrict the total character or number count allowed in that column. From here, the syntax establishes table constraints. The most critical of these is the primary key. The primary key is a unique identifier assigned to each row, ensuring no two records in the table can ever be completely identical. The code can also specify a foreign key, which links this table to the primary key of a completely different table. Enforcing these connections writes the physical links required to execute Codd's original relational model. The create table command holds 0 information. It simply constructs the strict, impenetrable vault that dictates how future data must behave. Once that architecture is locked, data can finally be loaded into the grid using the insert into command. The syntax begins by declaring insert into and explicitly naming the target table. It then lists the specific fields where the incoming information will be deposited. The code concludes by declaring the values themselves, the actual numbers or text intended for storage. The order of the provided values must perfectly match the order of the fields defined just above them in the syntax. Before storing anything, the SQL engine checks the incoming values against the previously established data types. If a single value violates an architectural rule, like an incorrect data type or a duplicate primary key, the entire insert operation fails and nothing is recorded. Insert into is completely dependent on create table. The data is entirely subordinate to the structure. This creates a strict operational sequence, defining the logic, building the structure, and finally loading the data. This exact sequence is identical across almost all relational database platforms in use today. In the 1970s, managing large arrays of shared data was an intractable problem of scale and chaos. SQL solved it by applying a standardized mathematical approach to information storage. Later commands used to retrieve or modify information, like select or update, only function because this rigid architectural foundation exists. Mastering these foundational commands is the first step in understanding the logic that governs how nearly all relational information is organized and stored.